Alright, this is a video for Precalculus, Section 1-2, Part 1. So we are looking at functions and their properties, and there's a lot of properties in this section. So we're just going to go over some properties that you probably already know just as a review. So most of these are probably going to be familiar to you. So functions, remember, we got the lovely function machine here. A function from a set D, that's our domain, to a set R, that's our range, is a rule that assigns to every element in D a unique element in R. And the set of D of all input values is the domain, and R are the output values, which are the range. Okay. So an important idea here is every number in the domain goes to only one number in the range for it to be a function, right? So these are mapping diagrams, and a function can only map an x value can only map onto a y, one y, right? So there's a problem. This one's fine. Every x only has one arrow going to one y. But over here, this one's not fine, right? This is not a function. Do you see which one? It's this x value right here, which they call x1. It's going to y1, and it's going to y3. That's not cool. All right, can't do that. Now, over here, y3 had two arrows going to it. That's fine, no problem. But this is the bad part. Okay, that's what makes this not a function. All right. Of course, you probably remember something called the vertical line test. The vertical line test is just a graphical representation showing how that definition of a function worked. The vertical line test says a graph, a set of points x and y in an xy plane, a coordinate plane, defines y as a function of f or of x if and only if no vertical line intersects the graph in more than one point. Because if you have a vertical line that intersects a point, you have one x value going to one y value, right? But here, we have an x value, whatever x value it is, he's going to 3 different y values. That's not a function. So this one's good, this one's good, no go. Okay. Now when we're talking about domain, there's two kinds of domain. There's implied domain and there's relative domain. So let's look at the difference. Unless we're dealing with a model like volume, so like a real world situation that necessitates a restricted domain, we'll assume that the domain of a function is defined by an algebraic expression is the same as the domain for the algebraic expression. Okay. Now for models, they have a certain domain that fits the situation. So for example, if we're talking about the volume of a sphere, so 4/3 pi r cubed. The domain of this variable here, r, is restricted not in an algebraic sense, but in a real world sense. Because a sphere that has a radius, that radius cannot be negative and it cannot be 0. So just by the sort of the fact that it can't happen, because it doesn't make sense for the real world situation or the modeled situation, we do set a relevant domain on this and we say r must be greater than 0. I almost put an equal to there, but that shouldn't be true either, because if your radius is 0, you don't have a sphere. Alright. So let's look at some domains. This is alternative examples 3, so you can look at regular examples 3 from your book. We're finding the domain of each function. When we're finding a domain, there's a couple of things that we have to really pay attention to. This is not an exhaustive list, but they're two common things. First, denominator cannot equal 0. So any value that will make a denominator 0, that is out of the domain. All right, if you remember hyperbolas, they give you a vertical asymptote there. Another thing is we cannot take square roots or any even indexed roots. So if n is even, then the thing underneath the radical called the radicand cannot be negative. So in other words, no negative even roots. So you can't take a square root of a -3, right? I know it's an I thing, but that can't be in our domain. Imaginary numbers are not in our domain for the xy coordinate plane. And the same thing if this was like a fourth root of the square root of -3. No go on that. Now there's other cases, as you know, with logarithms and exponentials and other special cases that we need to consider. But these are the two biggie, all right? And they're definitely happening here. So for the first one, I have an even root. I have a square root. So my square root of x plus 4, I know that the inside x plus 4, it could be a 0. So if I have a -4 in there, I could take the square root of 0, no problem. But anything less than 0 is a problem. So I'm going to set this inequality up. I'm going to say x plus 4 must be less than 0. And I'm going to solve it. So then I can just subtract it, and I get x has to be less than -4. Or actually, x cannot be less than -4. I'm kind of looking at what it can't be right now. I could reverse this around and say x has to be greater than or equal to 0. Right? So sometimes I think of domain as what can it not be? But then you can reverse it around and think what will it be allowed to be? It depends on the situation. So I think maybe this is a little better in this situation. I'm thinking, what can x be? X can be -4 or bigger. And that's just your domain. Everything bigger than or equal to -4. Or in interval notation, -4 bracket, comma, infinity. Okay, let's look at the next one here. Let's make some room. The next one here, we have two things going on. We've got a square root, but then we also have a denominator with a variable in it. So right off the bat, the denominator, I know x cannot equal 3. The numerator, I know again that x must be greater than or equal to 0. So both of these things needs to happen. We'll look at the graph of this in a bit to kind of see what happens here. So our domain is, one way you can sort of combine this is you can say all non-negative real numbers except 3. That would get everything you need. Non-negative, right? That allows 0. That's fine. There's nothing wrong with 0. I can plug in 0 in the denominator. It gives me a -3 in the denominator. No biggie. So that includes 0. That includes positive numbers, except for 3. All right, let's look at C. C, you'll notice, has a little bit more text to it because it's a formula almost. It says a of x is equal to x squared, where a of x is the area of a square with sides length x. So we're talking about area. This is a model. Now in general, if I just gave you this and I didn't tell you any of this area stuff, your domain would be this. Everything. There's nothing you cannot square. Everything in there, fine, no problem. But because of this modeling, we have to limit it. If x is the length of a side, then it must be greater than 0. It can't be negative, it can't be 0. So then x is greater than 0 would be our domain a relative domain. This is a relative one. It's relative to the situation. Okay, so let's look at what these graphs look like, and we can kind of see. So here's our first one. This was f of x equals the square root of x plus 4. And we said that the domain was x is greater than or equal to negative 4. So if we look right here, there's negative 4, and the graph hits it. Okay, so our domain, sometimes I like to highlight this to kind of see it, is everything from negative 4 on. But nothing over here, right? This is bad. I cannot plug in negative 5. That's why the graph doesn't go over there. Okay, the second one, this was g of x, I think it was, equals the square root of x over x plus 3. So we said two things. Oh, sorry, minus 3. We said two things. We said we can't have a negative or a 0 in the denominator so that x cannot equal 3. And we also said that because of the numerator, x has to be greater than or equal to 0. So there's two things happening here. Remember, this right here, in the graphing programs, sometimes they draw a line, but that's an asymptote. That's where an asymptote should be. And the graph will not be there because of this. Now this part, you notice you have a branch here, and then you have a branch here, and it kind of just stops. It doesn't keep going. That's because of this part, because you can't plug in any of these negative numbers. So the graph won't show up anywhere over there. And so our domain is this all the way up until 3, and then everything bigger than 3. Okay, last one here. Now if you graph, this was just x squared, right? A of x is equal to x squared. But it doesn't know that we're talking about a, what was it, an area of a square. And so it just plugs in everything, right? It's going to plug in negatives. All of these negatives, negative 1, negative 2, negative 3, all of these get plugged in because it's fine in a square. I mean squaring, right? But it doesn't know we're actually finding, those are lengths and areas, and it doesn't know that. So it's just going to include it. Although our real domain is just this, from 0 on. That's fine for the situation. Okay, one more example we're going to look at is the range. Now range is harder than domain. You can kind of try and think it through, but sometimes it's just going to be easier to graph it. So range remember, are the y's, the outputs. So you have to think about what you're going to get out of it. Okay, now we can plug in every number we want here except for 0. So the domain is all real numbers except for 0 for x. Now the range, think about what you're going to get out. Just start thinking about, could I get positives? Sure. Could I get the number 2? Sure. Could I get the number 1? Sure. Can I get 0? How are you supposed to take 2, divide it by an x, and get 0? And remember, if we plug in 0, we don't get 0. We get undefined. We get something that's not the same as 0. So there is no real value of x here that would make this happen. It just doesn't exist. And so we get a horizontal asymptote, if you remember. Alright, this is y equals 0. Because, or I guess you could think of it as f of x equals 0, since we're using the f of x notation. So we can see the range is all y's except 0 also. Because 0 is not in the range. You can never get that out of this problem. Okay, that's it for this section.